Hello, this is Maria here, and today we will be discussing a new method that was found for the synthesis of nanofabrics, specifically with woven ligands. And here are the key points. Today we're covering the importance of nanofibers, as well as the difficulty of synthesizing nanofibers that have woven ligands rather than stacked ligands, the new method that was found, and its benefits, as well as further research that is needed. So, synthetic fibers and fabrics have become an integral part of many industries due to their cheap manufacture, especially when compared to naturally derived fibers. Nanofabrics in particular have wide versatility, from improving macro fabrics, as seen in the production and increasingly widespread use of Gore-Tex technology, as well as to aiding in pharmaceutical delivery. So, there are some difficulties with, different methods of weaving together molecules to make nanofibers. They can be either woven or stacked, and woven grids are more durable but more difficult to make. And once the nanofibers have been made into grids, they can be tessellated together to make a sheet of nanofabric. And the goal of this research was to make a woven two-dimensional polymer rather than an unwoven one-dimensional polymer or a woven 3D polymer. And grids with woven ligands had not been previously reported. The new method consisted of synthesizing a diethyl building block with alternating rigid aromatic and flexible aliphatic regions, as you can see here in that first little picture. And so the researchers started with a metal template synthesis, which is a good way of making complicated molecular structures such as molecular knots and links and intertwined structures. And these blocks were interwoven via metal ions, specifically iron ions, into a grid structure with Bf4- anions encapsulated within each of the little squares, as it's not shown here, but in the squares, as you can see. And the grids had ligand strands that were parallel or orthogonal, which is at right angles, to the other strands in the same layer. The grid was merely an intermediate in the synthesis of the molecular knot that was formed because the metal ions encouraged strand crossing. And so the diethyl was converted then into disulfides via oxidation, and these disulfides allow for the separate tiles or grids to be connected into a larger polymer sheet. As you can see here, they are then connected. And once the grids have been connected into a larger polymer sheet, the ions were then removed using demetallization methods, specifically potassium cyanide in this situation, thus creating a purely organic molecular fabric that was measured to be 4 nanometers thick. But it had a very large surface area, as you can see in this image of the flake that it has. Now, a few important characterizations of the new polymer include the discrete layers that it has, the horizontally offset layers, the tiled arrangement of interwoven grids, and parallel arrays of strands. The offset layers were effective at connecting the interwoven grid tiles, as well as in conjunction with the anions and the bulky isopentyl groups, which you can see back here again up at the top. There's the isopentyl groups. The offset layers and anions and bulky isopentyl groups between grid layers prevented strand connections between the layers so that as to not make a 3D polymer from forming. Although there may have been some disulfide linkages, but those were insignificant. The product was able to be isolated as a large, very thin, flaky, nanosheet, even without standard exfoliation methods such as manual grinding or sonication. As you can see here, there's the very nice flaky nanosheet. The woven ligand strands were able to cover small gaps through reptation, which is slithering movements, reptilian, if you will, within the weave. And so when there were any small gaps, such as an absence of an individual tile, which was rare, the woven ligand strands were able to cover it up and make it even less noticeable. And because of the woven architecture and long-range order, which long-range order is regularity over distances greater than just 1 or 2 atom spaces. So in compared to crystallization, it's much larger region. The woven architecture and long-range order allowed the two-dimensional woven nanofabric to react to strain in a similar way as to macroscopic fabrics, specifically cracking along clear lines and slipping between layers. Also similar to macroscopic fibers, this nanofiber had a box weave pattern, which we covered before and which you can see here with it alternating up and down. And it was loosely woven but had flexible and rigid segments. So those are some of the benefits of the new method, but also the benefits of the woven nanofiber include, in comparison to the non-woven linear polymer, the two-dimensional woven polymer had a flake-like structure and larger surface-to-volume ratio, which allowed it to oxidize faster in air and in an inert atmosphere. To understand the incredible surface dimension area achieved, the woven polymer was measured in micrometers for length, but nanometers for thickness, a difference of 3 orders of magnitude. And the 2D polymer was more stiff, determined as having a Young's modulus of 7 gigapascal. Nylon and other polymers had moduli of 2 to 4 gigapascals. Additionally, the two-dimensional nanofiber was better at filtering bigger molecules, specifically iron 2 circular helicate, than the one-dimensional polymer, although both were able to similarly filter a smaller iron 2 phene complex. And again, in comparison to the one-dimensional, the two-dimensional has the box weave pattern and the long-range order. And so lastly, we can do some further research with finding how to stabilize the woven polymer by preventing individual sheets from sliding apart, and possibly also preventing against oxidation, as that could deteriorate it. And also to see the full range of applications of the two-dimensional woven nanofiber, specifically which specific ions or specific sizes of ions would be allowed through the net-like structure, and what applications does it have compared to nylon and other polymers, especially with regards to its stiffness. And here are my references, and thank you so much for listening.